Our last amplifier that we need to look at is the common collector or emitter follower amplifier. It is more commonly called an emitter follower than a common collector, but I prefer the common collector nomenclature because it fits in with all of the other ways that we've classified our quantities, right? So for a common collector amplifier, our baseline configuration is going to look something like this. We have a power supply voltage connected directly to the the collector terminal of our BJT. At our emitter terminal here, we have a resistor RE. We are taking the output at our emitter terminal, and we are applying the input at our base terminal. So the small signal model for this configuration is going to look like this. Let's put our base terminal here. Here's our resistance R pi and its associated voltage drop VBE. Here is our emitter terminal. Then we have GM VBE here and our collector terminal. So between the emitter and ground, we have some resistance RE, and the voltage drop over that emitter resistance is the quantity V out. Between our collector and ground, we just have a short circuit since our power supply VCC is an AC ground. And between our base and ground, we simply have the quantity V. So here is our small signal model. Anybody have any questions, comments, concerns about how we've drawn this? So, as per usual, we are going to determine the input resistance, the output resistance, and the voltage gain for our amplifier. Luke, you're making hand gestures. You okay? Okay. If I screwed up, I want to know. So to determine our input resistance, I'm going to redraw this circuit slightly. Okay, I'm going to give it the old circuits one treatment because, again, that's how my brain mostly works. So on the left-hand side, I have V in. Then I have my resistor R pi, over which a voltage drop VBE occurs in the positive polarity, of my voltage VBE corresponds to the positive polarity of my input voltage. So this node right here looks like my emitter terminal. Between the emitter and ground, I have that resistance RE. Where this down here is my ground terminal. And then between the collector is our ground actually. And so between the collector and the emitter, I have my dependent source, GM VBE, and the direction of my current is up because it's flowing from the collector to the emitter. We all okay with that? So this is my current I in. I can simplify things a little bit here. I don't know that it's entirely necessary, but I can simplify things a little bit here by doing a simple source transformation. Since I have a dependent practical current source on the right-hand side, I can make this guy a single loop circuit and then just use good old KVL and Ohm's law to figure out what that quantity I in is. So performing that source transformation, all that's going to do is move that resistor RE from here to here, and it changes that current source to a voltage source having a value of GM VBE times that resistance RE. Everybody okay with that? So from this, we can see that my input voltage Vin is just R pi times IN plus RE times IN plus GM. So what's VBE going to be? R pi times IN, right? Multiplied by RE. And from this, RN, which is Vn over IN, will be R pi plus RE plus GM R pi RE, which can be expressed as R pi plus beta plus 1 times RE, where we're recognizing that the quantity GM times R pi is exactly equal to beta. So anybody have any questions regarding our input impedance calculation? Arguably one of the more straightforward ones. Okay. Nobody is saying they're having difficulty, so let's look at this guy right here. When we determine our output resistance, what do? We short out the in, and then we apply a test source at our output terminal, which means we're just going to have a test source applied across the terminals of this resistor R. Okay? So I'm going to circuits one this up, but I'm going to explain to you what I'm doing. So I'm going to have a voltage source between this point, the emitter, and at this point down here, ground, which means my voltage source is directly in parallel with the quantity RE. It's also going to be directly in parallel with the quantity R pi, right? And it's going to be in parallel with my current source as well. So for the determination of R out, what it's going to look like is this guy. So here we have our test voltage in parallel with RE in parallel with R pi. And here we have our current source, GM VBE, like so. So the only thing I really need to check here is the polarity of VBE. So let's just do that real quick. So remember, I'm placing my test voltage source positive polarity up here at the emitter, negative polarity at ground. So the positive polarity of my test voltage source corresponds to the negative polarity of my quantity VBE. So that's negative. Like so. Here's my quantity I test that I'm trying to figure out. And I can see that I test is simply V test over RE plus V test over R pi minus VM VBE, where obviously VBE is simply negative V test. And from this, I can see that I test over V test is 1 over RE plus 1 over R pi plus GM, which means R out is simply RE in parallel with R pi in parallel with 1 over GM. So effectively, these three conductances in series look like these three resistances in parallel. Anybody have any problems, questions, comments, concerns about this one? All right. So the last thing that we need to determine is our voltage gain. Okay. So let's look at this guy right here. So the output voltage is just going to be the voltage drop over our resistor RE. Okay. Which means that it's just going to be RE times this current plus this current, right? So let me write this stuff down here. We're probably going to flip back and forth between those two things, right? So we can say that V out is RE times some currents here. So let's talk about the current flowing to the left or from the left. Let's call it this guy. So I'm going to call this current VBE over R pi. And when we talk about our current flowing from the right, that's obviously just GM VBE. VBE over R pi plus GM VBE, which we can make look like RE times 1 over R pi plus GM times VBE, and I'm trying to decide here. Yeah, I'm going to do this as well. So we know that GM times R pi is equal to beta, right? We used that before, I believe. Let me just double check to make sure I'm not talking out my butt here. Nope. Yeah, GM times R pi is equal to beta. And so I can rewrite this as RE GM beta plus 1 over beta times VBE. Right. So if I, just to be clear here, if I pull this GM out, I have 1 over beta plus 1, which is the same as beta plus 1 over beta. All right, so now let's look at what V pi is. Or excuse me, VBE. Sorry, let me do it this way. So from this, VBE is V out over RE times R pi over beta plus 1. Hold on, let me make sure I'm following my old notes for this to make sure this all makes sense. So I get dividing both sides by RE. Okay, yeah, so it's going to be a GM over beta, which is R pi. Yeah, okay, that makes sense. Sorry. So what I'm going to do now, let's scroll up here, is apply Kirchhoff's voltage law around this left-hand loop, right? So I can say that Vn is equal to VBE plus V out. Which is going to look like V out times R pi over beta plus 1 RE plus V out which is the same as V out times 1 plus R pi over beta plus 1 RE. And from this, my voltage gain becomes 1 over one plus R pi over beta plus 1 times a factor of 1 over RE. And if I multiply through by RE over RE, what this gives me is RE divided by RE plus R pi over beta plus 1. Okay. So this is the form that I prefer because it makes it very easy to see the voltage gain for this common collector amplifier is always less than 1. Okay. Now, depending on how large quantity beta is, it can look approximately equal to 1, right? This amplifier is how you make buffer amplifiers with BJTs. So we have a gain very close to 1, but we're able to add in input resistance and all that kind of good stuff to keep our signal clean. Okay, so this is a buffer amplifier scheme effectively using BJTs. All right. So now let's talk about what happens if we include the early effect. I'm going to scroll up here to the top, very, very beginning. Where is my early effect resistance R naught going to show up here? Always between my emitter terminal and my collector terminal, right? Or collector and emitter terminals. Okay. So if I drew that in blue, that's where my early effect resistance would show up. In my small signal analysis, what does this look like? I have a resistor connected between my emitter terminal and small signal ground, which just makes this R naught appear as if it's in parallel with the quantity RE. I don't need to do any new analysis whatsoever to figure out what the effects of, or to figure out what changes occur due to having my early effect resistor present. Literally just everywhere I see RE, put RE in parallel with R naught, and I'm good to go. Is that okay with everybody? All right. So now let's work on the permutations here, messing with it, making it arguably more complicated. So what if we have common collector with a signal or base resistance, and I can call it either of those because we're applying our input signal at the base, okay? So that would look something like this. Here's VCC. Here's V out. Here is, let's just call this RB. Oh, and I need to label this guy, so let's call it RE. So I feel pretty strongly that the input resistance is a fairly trivial thing to calculate, right? So what I mean by that, we call this quantity Rn prime, where we're looking directly into the base terminal at the point just past our base resistance. That's exactly the same as the input resistance we saw in our previous example, right? So if Rn prime is equal to R pi plus beta plus 1 Re, then obviously Rn is just Rb plus R pi plus beta plus 1 Re, because that base resistance appears in series with the resistance seen looking into the transistor. For our output impedance, I'm going to circuits oneify this thing. Okay. So effectively, we're going to have practically the exact same circuits one representation as our previous example, except that instead of seeing R pi connected directly to ground, we're going to see R pi and RB in series. So here is our test voltage, V test. Here is RE. This guy right here is R pi. Here's our VBE. Here's our quantity RB. And I'm drawing this guy up here because I want to talk about something in just a moment. Sorry. That is not remotely right. BBE. Can't read my own things. Let's call this quantity I test. And we can say that I test is V test over RE plus V test over R pi plus RB, minus GM. And then the quantity VBE, just using voltage division, is going to look like negative V test times R pi over R pi plus RB. From this, I test divided by V test looks like 1 over RE plus 1 over R pi plus RB plus GM times R pi, which is just beta, divided by R pi plus RB. And from this, our output resistance is RE in parallel with R pi plus RB over beta plus 1. So the thing I wanted to talk to you guys about, I'm going to have you prove this in a homework problem. What if we had put a collector resistance RC in this circuit? That collector resistance would show up right here. Would that change the value of our output resistance at all? Not even a little bit. Turns out that the presence of this resistance RC will not affect the input resistance, the output resistance, or the voltage gain of the circuit. Okay, I'm going to have you guys prove that. I just wanted to point out where you put it in. Stretching or raising your hand.
Does RC have negative effects?
So RC doesn't have any effect on the small signal operation of the circuit. What it has an effect on is the DC operating point of the circuit when we look at our fully biased circuit, okay? So if you can imagine here, and we're going to talk about the bias circuit next, but if you can imagine here, if we have like our voltage divider set up on the input side, right? Without RC in place, that means that VCE by definition will just be really large. So we are going to most likely, I mean, it's definitely, it's not a situation where we're definitely going to have the device operating in the forward active region because we don't have that feedback loop that literally forces that. But if it's operating in the forward active region, it's very deep in the forward active region, meaning we have a large value of VCE, and very likely we're going to see a large value of that early effect current that causes it to tilt up. Yeah. So this collector resistor effectively just stabilizes that. Or another way to think about it is if you have one of the terminals tied literally directly to the power supply voltage, that makes the transistor very sensitive to variations in the power supply voltage. That collector resistance kind of evens that out.
You said it stabilizes, so you prefer to have?
Yeah, well, why wouldn't you?
Okay.
Yeah. So it doesn't literally change anything for the small signal at all. And you have something to eat up a little bit of variations, right? Because if you don't have a resistor here, anytime the power supply voltage changes, VCE changes by however much the power supply voltage changes. With the resistor there, VCE only changes by the ratio of that current. All right. So our voltage gain. Okay. So we call this voltage VB. We know the relationship between V out and VB because we just derived it a couple of minutes ago. So what influence is having this resistor RB in place have? Just like all the others, makes a voltage divider at the input. So Let me label this as VB just for the sake of argument. So we know that V out over VB is equal to RE divided by RE plus R pi over beta plus 1. VB over Vn is going to look like R pi plus beta plus 1 RE divided by RB plus R pi times beta plus, or excuse me, plus beta plus 1 times RE. And when we multiply these two things together, the result simplifies to RE times beta plus 1 over RB plus R pi plus beta times beta plus, excuse me, plus beta plus 1 times RE. So again, we have a voltage gain that's probably going to be reasonably close to 1. It's definitely going to be less than 1, but close to 1. But the larger RB is, the smaller the voltage gain gets. All right. So lastly, let's talk about our biasing circuits here. There are two that are commonly used. So this is our first one. And then our second one is very similar, but effectively only contains one resistor connected at the base. Okay. So look at the one on the left first. At AC, that capacitor, and this should be CC1 as well, actually, is a short circuit, right? So what we would see is effectively our input voltage applied directly at our base, our output voltage taken at our emitter, and between base and ground, we would have R1 in parallel with R2. Is that going to change the input resistance of our core common collector amplifier. Let's talk about Rn here. How is it different at AC than this guy? Right, so the R1 and R2 would be between the input terminal and ground. So when we were looking in, we'd see R1 in parallel with R2 in parallel with this guy. Right? So if our input resistance is R pi plus beta plus 1 times RE, then we simply have R1 in parallel with R2 in parallel with R pi plus beta plus 1 RE. Right? I'm going to call this guy right here, just so that we're very clear. R in prime, where R in prime is what we see looking directly in to the base terminal, right? So does that make sense that it's just that in parallel with R1 in parallel with R2? So on the right-hand side, what's that going to be? Yeah, just RB by itself in parallel with what I have listed as Rn prime. What if I had a signal resistance? Right, so if there was a resistor between Vn and this capacitor. Distance here, yes. All right. Output resistance. What is this going to look like? So recall, the Vn is shorted. And the capacitor, so Vn is shorted to ground and the capacitor looks like a short circuit, which means this node right here is ground. This node is ground, so obviously R2 is shorted out. This node is ground, so R1 is also shorted out. Okay? So that means that the output resistance of this guy is just the output resistance of the common or most simplified version of this circuit that we analyzed at the beginning. So what was R out in that case? So RE in parallel with R pi in parallel with 1 over GM, all right? And for the right-hand side, literally the exact same thing. Okay. Voltage gain. Okay. So my input voltage is applied here directly at my base. which means I don't have a voltage divider circuit. So my voltage gain is going to be the exact same thing as the most simplified version as well, in both cases, right? Only if I included some signal resistance would I have to do that voltage division trick at the input, right? So this is going to look like, what is it, R pi, or excuse me, RE over RE plus something, right? And the voltage gain for the right-hand side is literally the exact same expression. Right. That's the multiple configurations of our common collector amplifier. How do you guys feel about this BJT based material? Seem wildly difficult or anything like that? So next week, we are going to cover MOSFETs. Okay. We are going to take the time to derive all the small signal parameters for MOSFETs and all that kind of good stuff, because we do need to have a solid foundation. But once we get to our actual amplifier analysis, it's literally this exact same stuff, except that we're going to have a different subscript on our resistors, okay? The only appreciable change in our small signal analysis is the fact that for a capacitor, excuse me, for a MOSFET, the thing between the source and the gate, much like the thing between here, the base and the emitter, is a capacitor instead of a resistance. So we're literally just going to be analyzing the exact same circuits where R pi goes to infinity. Okay. Because if it's a capacitor, it's got an infinite impedance. Okay. So we are going to pretty much fly through the MOSFET transistor amplifiers because it's literally the exact same circuits. Okay. So if there's any of this business that didn't make sense with BJTs, take our quote unquote long weekend, since we're not having class on Monday, to think about what kind of questions you might have. And then let's talk about those, because the MOSFET analysis is literally the same thing. Okay. All right. That's enough out of me for today.